Forced oscillations in power systems are relatively common events that have gained much greater awareness in recent years due to the use of phasor measurement units (PMUs). These oscillations can potentially impact equipment and operation negatively. A forced oscillation is an unintentional periodic exchange of energy across different components of a power grid. It is characterized by a set of frequency, damping, amplitude, and phase terms. The system response to a forced oscillation is the sum of the natural response and the forced response. The natural response is the portion of the response associated with the system, while the forced response is the portion of the response associated with the input. Forced oscillations reflect the characteristics of a periodic input to the system. The sources of these periodic inputs are varied and can include traditional generation, e.g., fossil, hydro, and nuclear plants, alternative generation, e.g., wind and solar, cyclical loads, e.g., aluminum smelting, and malfunctioning controls. The characteristics of forced oscillations include narrow frequency components, harmonics frequencies are integer multiples, and a consistent oscillation frequency throughout the system. The shape of the oscillation is observed in the amplitude and phase in different parts of the system. The appropriate action when a sustained oscillation appears depends on the oscillation's type. If it's a forced oscillation, the input should be disabled. If it's a natural modal oscillation, the system operation should be adjusted to improve stability. Understanding the fundamentals of forced oscillations is crucial for maintaining the stability and efficiency of power systems. It helps in identifying the sources of disturbances and taking appropriate actions to mitigate their impact. Forced oscillations occur when an external periodic input, such as an oscillating steam valve in a turbine generator, causes a power swing or any other reason. These oscillations have been known for years, but they have become more visible recently due to the installation of phasor measurement units (PMUs). The explicit formulation of the oscillation is formulated in terms of forced disturbances and system mode shapes. The forced oscillation amplitude, components, and envelope are intensively studied. Consequently, measures for mitigating the oscillation are obtained. Forced oscillation can also be effectively detected and discriminated from modal oscillation by utilizing its uniqueness of components' properties and envelope shapes. The origins of forced oscillation are sinusoidal in nature, including cyclic loads, electrical oscillations due to malfunction of power system stabilizer (PSS), and mechanical oscillations of generator turbines. The causes of mechanical oscillations are complex and strongly related to the thermal process. Forced oscillations can be caused by an external periodic disturbance or a mistuned generator controller. The origins of forced oscillation are sinusoidal in nature, including cyclic loads, electrical oscillations due to malfunction of power system stabilizer (PSS), and mechanical oscillations of generator turbines. The system response to a forced oscillation is the sum of the natural response and the forced response. The natural response is the portion of the response associated with the system, while the forced response is the portion of the response associated with the input. Forced oscillations can have significant impacts on power system stability. They exhibit extremely higher amplitude and may cause catastrophic blackout, especially in the poorly damped operating condition. The resonance between forced oscillation and electromechanical mode can cause system breakdown. Forced oscillation amplitude, components, and envelope are intensively studied. Consequently, measures for mitigating the oscillation are obtained. Forced oscillations in power systems can be caused by a variety of factors. Here are some examples. 1. Traditional generation. Fossil, hydro, and nuclear plants can cause forced oscillations due to the mechanical processes involved in power generation. 2. Alternative generation. Wind and solar power plants can also cause forced oscillations due to the variability of their power output. 3. Cyclical loads. Certain industries, such as aluminum smelting and steel plants, have loads that vary in a cyclical manner, which can cause forced oscillations. 4. Malfunctioning controls. A broken valve on a thermal unit or the operation of a hydro unit in a rough zone can lead to forced oscillations. 5. HVDC controller. The operating mode of a combined cycle plant or a high-voltage, direct current HVDC controller can also cause forced oscillations. These are just a few examples. The specific causes can vary widely depending on the characteristics of the power system and the nature of the disturbance. What is the difference between forced and natural oscillations? Forced and natural oscillations are two types of oscillatory motion that can occur in a system. Here's how they differ. Natural oscillations. These are oscillations that a system undergoes in the absence of any external force. They occur due to the elastic forces and inertia of the system. The system vibrates at its own natural frequency, also known as the resonant frequency. An example of natural oscillation is the swinging of a pendulum. Forced oscillations. These occur when an external periodic force is applied to a system. The system then oscillates at the frequency of this external force, which is known as the forcing frequency. Even though the amplitude of oscillation experiences damping, it remains constant due to the other external energy supplied to it. An example of forced oscillation is pushing a child on a swing. The key difference between natural and forced oscillations is the presence or absence of an external force causing the oscillation. How to mitigate the effects of forced oscillations in power systems. Mitigating the effects of forced oscillations in power systems involves several strategies. 1. Locating the source. The first step in mitigating forced oscillations is to identify the source of the oscillation. This could be a malfunctioning controller, a cyclical load, or even a cyber attack. 2. Use of battery energy storage systems BESS or inverter-based renewables IBR. These can be used to suppress the magnitude of forced oscillations. If the source cannot be located quickly, control can be activated to reduce forced oscillation energy. 3. Unified Power Flow Controller UPFC. A UPFC can be used to shift the resonant frequency, effectively mitigating the steady-state response of a forced oscillation. 4. Static Synchronous Compensator with Energy Storage, Enhanced StatCom. This device can be used to modulate active and reactive power, effectively eliminating forced oscillations propagating from the disturbed area to other areas. 5. Cybersecurity measures. As forced oscillations can be caused by cyber attacks, implementing robust cybersecurity measures can help prevent these types of disturbances. The appropriate action when a sustained oscillation appears depends on the oscillation's type. If it's a forced oscillation, the input should be disabled. If it's a natural modal oscillation, the system operation should be adjusted to improve stability.
Forced oscillations can be dangerous for several reasons. 1. High amplitude. Compared to natural oscillations, forced oscillations can exhibit extremely higher amplitude. This can lead to significant power swings in the system. 2. Resonance. When the frequency of the forced oscillations is close or equal to the natural frequencies of the system modes, resonance can occur. This can lead to large oscillations that can potentially damage equipment and destabilize the power system. 3. Confusion with modal oscillations. Forced oscillations can be confused with modal or natural oscillations. This can lead to incorrect diagnoses and responses to power system disturbances. Therefore, it's crucial to detect and mitigate forced oscillations to ensure the stability and reliability of power systems.